So today we're going to go through some of the proofs of how to show something is a supremum of a set. And I'm going to try and present things in a formulaic way so that when you're getting practice writing the proofs, you can follow these steps. So at several points during the lecture today, you will see problems for you to solve, and these are problems that will be due on homework next Friday. And in fact, in class on Monday, you'll get a chance to work on these problems and present them on the board. So let's start where we have a set A, where basically every element in A is 3 minus some quantity. So we've got 3 minus 2 over n plus 2, where n is a natural number. And what you should always do, I think, is just write down a few values. So we've got 3 minus 2 thirds, 3 minus 2 fourths, 3 minus 2 fifths. The idea is that we're subtracting less and less, and so things are going to get closer and closer and closer to 3. So our intuition says 3 is the least upper bound, and so to show that, we're going to go through two steps. So the first step is to show that 3 is an upper bound, and the next step is to show that we can't do any better than that. So in other words, if you said that the upper bound was smaller than 3, like 2.9, then I would have to convince you that 2.9 couldn't be an upper bound. So this might be a good time to pause the video and make sure you understand this second step here, because it can be confusing with the inequalities. Right? So great. We know that we want to show that 3 is an upper bound, so let's do that. So we want to show that 3 is an upper bound for A. And in this case, the intuition is clear, right? Every element of A is going to be 3 minus a positive number, so everything in the set is going to be smaller than 3. And I've shown you a way that I might write that. I might write, let x be an element of A, I will show that x is less than or equal to 3. So since x is in A, I have a description of it. I know that it's 3 minus 2 over n plus 2 for some natural number. And that means that x is 3 minus some positive number. So that means that x is less than or equal to 3. You might find your own way of writing this part of a proof, and you might want to send it to me and let me know if you have questions about it. So we've successfully shown that 3 is an upper bound for the set A. Now we want to show that if we take any number smaller than 3, maybe something like 2.9, then that's not going to be an upper bound for A. This will complete the proof, showing that 3 has to be the least upper bound. And again, I've got a picture here where we've got 3 and y. You see y is to the left. And again, our intuition says, hey, I bet I can find an element inside of A that's between those two. Because I bet I can pick n really big so that that point is really close to 3. So that intuition is great, but what we have to do is we have to sort of prove it rigorously, and we'll see that the Archimedean property is what's going to help us. So our scratch work is that, well, we just want to find n big enough so that when we plug it in, we get 3 minus 2 over n plus 2. We want that to be bigger than y. So we can take that inequality and we can solve for n. This might be a good time to pause the video and double check that your calculations are the same as mine. But basically, I start by subtracting y from both sides and moving that fraction to the right. I divide both sides by 2. Notice when I take the reciprocal of both sides, the inequality switches. That's really important. Remember, if we have something like 2 is less than 5, that means 1/2 is greater than 1/5. And as we go on, we eventually see that, oh, whenever n is greater than 2 over 3 minus y minus 2, then all of these inequalities will be true. And so we have our aha moment. The Archimedean property is going to tell us that we can indeed find a number n that's bigger than this. Okay? So the next step to do is to write it up. So we write up our proof and we say, well, if we had a number y that was smaller than 3, then by all my scratch work, I know that I want to take an n such that n is greater than 2 over 3 minus y minus 2. And this is going to mean that n plus 2 is going to be greater than 2 over 3 minus y. I repeat some more steps, eventually solving for y, and I'll see that, in fact, y is going to be smaller than 3 minus 2 over n plus 2. This shouldn't be surprising. This is exactly the inequality we started with when we went and found how big this number n had to be. So the grand conclusion is that y can't be an upper bound because we've found a number that's bigger than it. In other words, one that's closer to 3. So we finished our proof, and I have a problem for you. This is one of the problems on the homework, which is to find with proof the supremum of this set, where we've just taken 8 and we've subtracted 6 times n plus 5. And one thing I want to point out to you is that I could have not given you such a nice expression. I could have given you something like 8n plus 34 over n plus 5. And if I had done that, one problem you would have had to do would be to go backwards, to take this fraction here and split it up as 8 plus or minus something. This is something you'll get practice with in the remaining parts of the lecture. So one bit of advice that I might have for you is if you have, say, this problem on the homework where you do 6n plus 16 over n plus 3, actually, come to think of it, this might be the problem on the homework. I can't remember if the first one was. But the idea is that we're going to take that and we're going to write it as 6 plus something over n plus 3. It might be 6 plus, it might be 6 minus. But you can sort of think that through, and if this gives you some problems, what you could do is you could maybe go online and look for long division of polynomials. There will be many videos helping you find quotient and remainder, and that can be a help in this course. So that completes our proof for the supremum. I have a slide here that talks about the lower bound, so everything is analogous, but I want to go through this. So these are definitions you should maybe pause the video and write down in your book. In fact, even better, it might be to try and write down the definitions before looking at them. So we want to define a lower bound, and we also want to define a greatest lower bound. So in fact, it would be a great exercise to see if you get these right before looking at them. So a lower bound is just something that's smaller than every element in the set. So we say x is a lower bound for a if x is less than or equal to a for every element a in the set. And we say an element x is a greatest lower bound if x is a lower bound and any number bigger than x is not a lower bound. And we might write that with symbols here saying if y is greater than x, then y is not a lower bound. So similarly, we can define the infimum of A. So if we have a set, then we define the infimum of A to be the greatest lower bound if A has a lower bound, or we just define it to be minus infinity. So for example, if A were the set minus 8 to 18, that open interval, the infimum would be minus 8 because that's the greatest lower bound. If B were the set 6 plus 1 over n plus 2, then the infimum of B would just be 6, because that's the everything's getting closer and closer to 6, and that's the greatest lower bound we can have. However, one thing to be careful about is that if our set were, say, 6 minus things, then everything is actually smaller than 6. So 6 won't be a lower bound. And if we want to find the lower bound, then we have to do a bit more work. So in this case, we look through and we see that the first term is 6 minus a third, then 6 minus a fourth, then 6 minus a fifth. And what that means is that, well, the smallest of those is going to be the first one, because we've subtracted the most. So in that case, this is going to be the infimum. And as we saw in class, whenever the supremum or the infimum is in our set, to complete the proof, we just basically have to show it is in this case, a lower bound. So now I want to finish these slides by doing a final proof. So I want to prove that the infimum of a set is 10. And so I've described this set as a fraction, 10n plus 32 over n plus 3. And we're going to have to do a little bit of work with these fractions, so we'll get practice with that. So I want to show that 10 is a lower bound, and I want to show that if y is bigger than 10, then it can't be a lower bound. So how do we do that? Let me close all these other ones quickly. So the way the proof is going to go is first we just need to show that 10 is a lower bound. So if we split the fraction up, we guess that it's 10 plus or minus something. We can see that if we put a 2 there, then everything would work out. So if x is an A, then x has to be greater than 10, because every element in A is going to be 10 plus something. And now we want to show that if we take a number bigger than 10, then y is not a lower bound. So again, this time we've chosen an element y that's to the right of 10, and we're going to again find some element in A, that's this thing up here, that will be in between. So again, our scratch work is that we want 10 plus 2 over n plus 3, that's our element in our set. We want that to be smaller than y. And so we go through some algebra to solve for what n needs to be. And again, we see if n is greater than 2 over y minus 10, all minus 3, then that will mean that this inequality above will be true. So this is a good point to pause the video. My battery is dying, so I'm going to finish quickly. But the only thing left is to write up the end of the proof. We start with the Archimedean principle by finding an n so that n is greater than 2 over y minus 10. And at the end, we've found an element that's less than y, so y isn't a lower bound. So I should stop here because I want to make sure I can save the video before my battery runs out. But there's a similar problem on the homework, and here's a hint. Thanks.